So friends, in today's session we are going to understand about very important topic known as Mohr circle method. The Mohr circle method is used for analysis of stress transformation by using a graphical technique. So it is a graphical method of analyzing stress transformation in the body. So before understanding graphical method of analyzing stress transformation, we have already completed in our previous classes the analytical method of stress transformation. So kindly go through previous lectures where we have tried to understand the analytical method of stress transformation. So just to give you a brief outline of the analytical method, let me just explain you what are the outcomes of the analytical method. So this particular element represents a two-dimensional object. This two-dimensional object is subjected to two-dimensional stress system. The normal stresses acting on its faces like sigma xx, which is acting in x direction. We have another normal stress sigma yy. The same normal stress is going to act here, and we have same normal stress acting as sigma xx towards left hand side. So we have normal stresses acting on the faces of this two-dimensional object, and we also have the shear stresses acting on these faces. So this is the shear stress which we call as shear stress, that is tau xy. This shear stress is called as tau yx. This will be same as tau yx, and this is tau xy. So we have the normal stresses as well as shear stresses acting on the faces of two-dimensional body as shown over here. Now we would like to find out the value of the stresses acting on some plane. Okay, suppose if I take this as a reference plane, plane AB. Now, so if you take a plane AC which is inclined at some angle theta, so plane AC is making an anti-clockwise angle with the reference plane AB. So we are interested to find out the stresses acting on this inclined plane. So what is the value of normal stress and shear stress that act on this particular inclined plane AC? So we wanted to find out the normal stress and the shear stress acting on the inclined plane AC. So this is what we call as stress transformation. So we have done the analytical method and we got the expression for normal stress and shear stress acting on the inclined plane, which is sigma normal equals sigma xx plus sigma yy by 2 plus sigma xx minus sigma yy by 2 cos 2 theta and tau xy sin 2 theta. Please remember the value of tau xy is same as the value of tau yx. Their magnitudes are equal, only their directions are opposite. Means this tau xy represents the anti-clockwise shear, while tau yx represents the clockwise shear. Okay, so tau xy is going to rotate the body in the anti-clockwise sense, while tau yx is going to rotate the body in the clockwise sense. Also, we have the expression for the shear stress acting on inclined plane as tau s, which is minus of sigma xx minus sigma yy by 2 sin 2 theta and tau xy cos theta. So this derivation we have already done. So kindly go through the previous videos where we have discussed in detail the derivation of these two expressions. Now this is all about the analytical method of stress transformation. Now this stress transformation we can also perform by using the graphical technique called as Mohr circle method. Now there exists a sign convention here. You have to follow the sign convention whenever we are using the analytical method. So as far as these two expressions for normal and shear stresses are concerned, we follow some sign convention as follows. So let me list them down. So the first sign convention here is sigma xx, sigma yy. They are normal stresses acting on the planes of two-dimensional element. So these are positive for tensile and negative for compressive conditions. For example, sigma xx is tensile, then we will take sigma xx is positive. If sigma xx compressive, then we take it as a negative. This is important sign convention. The second sign convention is for shear stress. So we only take shear stress of tau xy because we have only used tau xy in the expression. So for tau xy, if it rotates the element in the anti-clockwise direction, then it is taken as positive. So if the shear stress causes anti-clockwise rotation of the element, it is taken as positive shear stress. But if it causes clockwise rotation of element, then it is taken as negative. So this is a sign convention we are going to use for tau xy. And the last and very important thing, the plane, the inclined plane has to make anti-clockwise angle with the vertical plane AB. So it is about the inclination of the plane, that is theta. So there is an important sign convention for theta, that is, if plane AC, which is the plane on which we want to find normal stress and shear stress, is inclined with plane AB, which is a reference plane, and then if angle is anti-clockwise like this. So for anti-clockwise angle, it is positive. Anti-clockwise inclination is taken as positive. And if it is clockwise, clockwise means if this is the plane AB and our plane is inclined like this or like this. So the inclination is like this or this way. These are all clockwise sense. It is B and this is A and this is C, for instance. So this kind of position of the plane, so that is called as clockwise inclination. So if it is clockwise inclination, you will have negative sign convention. So theta will be minus theta. So these are a very important sign convention we follow in case of analytical method for stress transformation in the body. Okay, so this is a brief of what we did in the analytical method of stress transformation. Now, and we would like to perform what you call is a graphical method. So I'm going to use these two equations. So first one is the expression for normal stress on inclined plane, and the second one is the expression for shear stress on inclined plane. These two expressions I am going to use and try to develop a graphical method of stress transformation. Okay, so let me just clear one very important thing over here, that we wanted to generate a equation from these two equations in which there is a variation of normal stress and shear stress with angle theta. So when you change the position of plane, we should be able to get the value of the normal stress and shear stress acting on it. Okay, now second point is, if you look at this equation 1 and equation 2, the value of sigma xx and sigma yy are the stresses acting on the faces of two-dimensional object. So the value of sigma xx and sigma yy are fixed. They are acting on this plane. So these values are not going to change. Only the variable over here is the shear stress acting on inclined plane and normal stress acting on inclined plane. So the important thing is sigma xx, sigma yy and tau xy are not going to change. They are constant values. They are acting on these planes. So the variable is only theta, normal stress and shear stress, because we are going to change the position of the inclined plane. Okay, so let me just take this first equation. We can assume that sigma xx and sigma yy are constant. So sigma xx plus sigma yy by 2 is also constant. So we can assume this as a constant value A. Similarly, sigma xx minus sigma yy by 2 is also constant. So we can assume this is another constant value B. And as we have discussed, the shear stress acting on the faces tau xy is also fixed. That is called as C. So we've got three constants. So let's say let sigma xx plus sigma yy is A, sigma xx by 2 B, and tau xy, which is a constant, as C. So these, after doing these assumptions, we will get the simplified expression for normal stress acting on inclined plane, which is A plus B cos 2 theta plus C sin 2. So this can be simplified further. So we can write down this. We can bring A in the left hand side. So we can write down sigma normal minus A equals B cos 2 theta plus C sin. So this is a new equation we got. So let me just call this as equation number 3. We can use it later on. Similarly, we can also take the expression of shear stress. So let me bring the equation of shear stress here. So we have equation of shear stress, tau s equals sigma xx minus sigma yy by 2 sin 2 theta, tau xy cos 2 theta, but we have assumed sigma xx minus sigma yy by 2 as B and tau xy as C. So we can simplify this equation, minus B sin 2 theta plus C cos 2 theta. So This can be called as equation 4. Now our objective is to get an expression by using equation 3 and equation 4, and we would like to eliminate theta from both two equations. So what I will do is square and add both sides. Squaring and adding. So if you want to eliminate theta from both equations, so we shall get the resultant expression in terms of normal stress and shear stress. So we can find out the equation of normal stress and shear stress variation. So if I do squaring and adding, it will be like sigma normal minus A the whole square plus shear stress the whole square equals B cos 2 theta plus C sin 2 theta the whole square plus minus B sin 2 theta plus C cos 2 theta the whole square. So you have to simply do the algebra and expand this. So it is going to become B square cos square 2 theta plus C square sin square 2 theta plus 2 into B into C cos 2 theta sin 2 theta. That is first part. Then second part you will be getting B square sin square 2 theta plus C square cos square 2 theta minus 2B C sin 2 theta cos 2 theta. Very simple algebra of expansion. So if you look at here, this is plus 2BC cos 2 theta sin 2 theta. This is minus 2BC sin theta cos 2 theta. So both of them can be cancelled out. Here if you look at, this is B square cos square theta and this is B square sin square theta. So you can take B square common, and if you look at this is C square sin square theta 2 theta, and this one is C square cos square. So we can take C square common, these two. So if you simplify, the whole thing will turn out to be like this. So when I take B square common, there will be cos square 2 theta, sin square 2 theta will be there, but sin square 2 theta plus cos square 2 theta is going to be 1. So we will be getting simply B square here, and similarly for C square we will be getting sin square 2 theta plus cos square 2 theta. So remaining would be C square. So the right hand side would be simply B square plus C square, or we can simplify that as square root of B square plus C square and then whole square. So this is the equation which gives you the variation of normal stresses and shear stresses on the inclined plane. So as you keep on changing the position of inclined planes by changing the theta, you will be getting the variation of normal stress and shear stresses on it. So this is what we got. So this is the equation of stress variation with the variation of plane, right? Now we would like to understand a very important thing here, and that is equation of a circle having center on x-axis. So let me show you a circle having center on x-axis. Now if you look at here, I have drawn a circle having center on x-axis. Center of the circle is on x-axis. So let me say C is the center of circle. So the coordinate of C is going to be, since its center is on x-axis, it will have some value of x. So it will have some x coordinate. So let's say the x coordinate is h. So it is going to be h here. And since center is on x-axis, the y coordinate is going to be 0. So we have got a center of circle on x-axis. Let's say the radius is r. So if you take any point on the circle having coordinate x comma y, the equation of circle is given by x minus, the center has x coordinate as h, so x minus h square. Now y coordinate of center is 0, so it is only y the whole square equals radius square. So this is the standard equation of circle having center at origin. So the equation of circle having center on x-axis is given by x minus h square plus y square equals radius square. This is clear, right? Now if you compare the equation of circle having center on x-axis and the equation of the variation of stresses in the stress transformation. If you compare both equations, they look like very similar. Only difference is that instead of normal stresses we have x coordinate, and instead of shear stresses we have y coordinate. So it means, so by comparing these two, we can conclude that the variation of normal stress, that is sigma n, and shear stress tau s on inclined planes in the body. Which body we are talking about? We are talking about this body. So the variation of normal stress and shear stress on inclined plane in the body, right, is given by an equation of circle, and that circle is called as Mohr circle. That's very important thing. So we have a Mohr circle which gives you the variation of normal and shear stresses on the inclined plane. So this Mohr circle will have x-axis as what? Normal stress. So Mohr circle has following points. It has normal stress on, here you can see that x minus h, and here we have sigma n minus a. So instead of x we have sigma normal. So along x-axis we have normal stress. Normal stress, that is sigma n along x-axis. If you see, here it is tau s and here it is y. So shear stress along y-axis. We represent shear stress along y-axis in the Mohr circle. What else we have? Now the center of this circle is on h comma 0. So h is this one. Here h we have, here we have a. So it is going to be a comma 0. So center of Mohr circle would be, if you compare both equations, you will get a comma 0. So a comma 0. But we have already seen in the previous derivation that we have assumed sigma xx plus sigma yy by 2 as a. So the center would be at the value sigma xx plus sigma yy by 2 comma 0. What about radius of Mohr circle? So if you see here, here radius is r, while here radius is square root of b square plus c square. So the radius of Mohr circle is, radius, that is r of Mohr circle, is going to be square root of b square plus c square. Now if you look at here, we have taken value of b is sigma xx minus sigma yy by 2 and c is tau xy. So we can put that corresponding value, sigma xx minus sigma yy by 2 the whole square plus tau xy the whole square. So by using these salient points, we can locate the center of Mohr circle, we can locate the radius of Mohr circle. Once we got center and radius, we can draw the Mohr circle. So let me draw the Mohr circle here. So for Mohr circle, along the x-axis we are going to have normal stresses. So we are going to plot normal stress along the x-axis, and along the y-axis we have shear stress. Positive x will have plus normal, that is tensile normal stress, and here we will compressive normal stress. Similarly we will have tau xy positive shear stress. So, and this is going to be minus xy. So we have already discussed about the sign convention for what we call shear stress. So positive shear stress tau xy and negative shear stress minus tau xy. Positive normal stress, negative normal stress. So this positive normal stress means tensile. We have already done the sign convention. This is a tensile, friends, and obviously it is going to be compressive. Here plus tau xy is basically anti-clockwise rotation of element. So when element rotates in the anti-clockwise, so it is plus. So clockwise is going to be minus. Right? So these two are very important sign conventions. So now we would like to draw the Mohr circle. So I am going to locate the value of center. So first I will locate the center. The center of the Mohr circle is going to be at point which is sigma xx plus sigma yy by 2 comma 0. So y is 0, and then we are going to locate the radius. So value of radius is going to be some value. So we are going to locate the radius. So value of radius is r is going to be, as we have done, square root of this, square root of sigma xx minus sigma yy by 2 the whole square plus tau xy the whole square. So this is the value of radius of the Mohr circle. So once you got center and the radius of Mohr circle, you can plot the Mohr circle. Okay, so this is basically Mohr circle we have got. So we first locate the center of Mohr circle, and then we put the value of radius, and then we can draw the Mohr circle. So friends, this is the Mohr circle what we have got here. Now once we got the Mohr circle, we can find out the parameters required. What is the point on the Mohr circle? That is very important. So if you take any point on the Mohr circle, what is the meaning of the point on the Mohr circle? So basically, the point on the Mohr circle is nothing but it will have some x coordinate and it will have some y coordinate. So the x coordinate is going to represent the normal stress, and y coordinate is going to represent the shear stress, the value of normal stress and shear stress. Okay, so it means a point on the Mohr circle represents the combination or order pair of normal and shear stress. That means it represents the inclined plane in the body. Points on the Mohr circle represents the various combination of normal and shear stress, and the various combination of normal and shear stress is basically represents the various planes, various inclined planes in the body. So each and every point on the Mohr circle represents various inclined planes. So that is very important point I would like to make here. So the point on the Mohr circle represents an inclined plane in the stress body having normal and shear stress. Now the very important thing, so there are few points which needs to be understood. So first point is this point where Mohr circle is intersecting the x-axis or normal stress axis. So where it is intersecting the x-axis, at those points, let me call this point as point 1 and this point as point 2. So at point 1 and point 2 where the Mohr circle is intersecting the normal stress axis, there won't be any value of shear stress, right? You can see here because this does not have any y coordinate, so y represents basically the shear stress. So point P1 and P2 represents two planes which have only normal stresses. So by definition, you just go through our previous classes where we have discussed about the principal plane. So these points P1 and P2 represents the principal plane in the body. So point of intersection of Mohr circle with x-axis. X-axis is nothing but normal stress axis, represents principal plane. So these two P1 and P2 are the principal planes in the material or in the body, right? So the corresponding normal stresses would be called as principal stress. So this way we can understand that the variation of stresses in the body can be represented by an equation which is a equation of circle having center on x-axis. This circle is called as Mohr circle. The Mohr circle basically represents the variation of normal and shear stress on inclined planes in the body. So if you change the planes, various planes in the body, how the normal and shear stresses are going to vary in the body. And normal stress is represented along x-axis, shear stress along y-axis. The center of Mohr circle is at point sigma xx plus sigma y by 2, 0. The radius of Mohr circle is given by this expression. Each point on a Mohr circle represents a particular plane in the body. So number of points represent the number of planes in the body, and on those planes normal and shear stresses are going to act. There are two planes on which there is only normal stresses are acting, and those two planes are P1 and P2. That is intersection of normal axis with the Mohr circle. Those 2 points represents principal planes in the body. So I think we have understood what is the basic concept of Mohr circle, and by using this basic concept of Mohr circle, we shall be able to perform the analysis of stress transformation. So in subsequent classes, we shall be doing the analysis of stress transformation with the help of Mohr circle. We will try to find out normal and shear stresses acting on inclined planes by using the Mohr circle method or the graphical method. Thank you very much.